Assalamualaikum warahmatullahi wabarakatuh. I am Dr. Nashr Fazli Muhammad Nasir, and for our course ENT 405 Biosensor and Biomems, I will be teaching the other part of the lecture, which is the biomem section. And this biomem section will cover the photolithography, soft lithography, electrobeam lithography, micromachining, material position and bonding. Inshallah, we will have our online lecture, but for now, I will give you some information on the slides. Inshallah, I will try to teach this course in English, but if you have any questions, okay, we may have a bilingual discussion, okay, but I will deliver this inshallah 100% in English since we have our international student here. Okay, so what is actually MEMS? It's all about. Okay, first of all, we need to see the abbreviation of MEMS. Okay, MEMS means micro electromechanical systems. Okay, and this term originated from the US, United States. Okay, in Japan, it is referred as a micro machines, and in Europe, it is also referred as a microsystem technology, or MST. Okay, so now the first thing I need to remind you, okay, how you are going to remember what is MEMS. Okay, first of all, there are three phrases that you need to remember. First of all is the, okay, it is a process. Okay, MEMS is a process technology, okay, used to create tiny integrated devices or systems, okay, that combine mechanical and electrical components. So if a questions come out about what is MEMS, okay, it is a process technology, okay, and then you create tiny things, okay, tiny integrated devices or systems, which, okay, and then we go and refer to the name itself, okay, to the term itself, which combine mechanical and electrical components. Okay, the other parts, okay, the other parts that you need to know that it is fabricated using integrated circuit. Okay, fabricated using integrated circuit batch processing techniques and can range in size, okay, from few micrometers to millimeters. Okay, so what are the function of these devices? Okay, it has, okay, the system or this device has the ability to sense, control and actuate. Okay, so it has three functions there: sense, control and actuate on the micro scale. Okay, must be in micro scale, and then generate effects on the macro scales. Okay, so if let's say a questions come out, okay, like for instance biomems, what you are supposed to answer? Okay, biomems means that a process technology used to create tiny integrated devices or system that combine mechanical electrical components used for biological applications. So that's the meaning of biomems. Okay, and then you can substitute for other things, like for instance agromems and so on. So okay, but the first thing that you need to remember is, okay, there are three components, okay, in the terms, which is the process technology, okay, used to create tiny integrated device or systems, okay, and it combines, okay, mechanical electrical components. So that's the thing that you need to remember. Usually, the work related to MEMS or biomems will be done in a clean room. Okay, will be done in clean room. And now, as you know, like, okay, you will wear something like a COVID, okay, the frontliners for the COVID-19 lah kan. Okay, you will wear the clean those suits. Okay, so these, okay, clean rooms, okay, should have less than 100 particle, okay, per meter square. So it is very clean. Then we have a reason why it has to be so clean. Okay, so in the fourth slide, okay, you can see the standard clean room garment. Okay, standard clean room garment. So what is the difference between, okay, for if you can see the picture, okay, depicting a frontliner, okay, to handle the COVID-19 virus, okay, it it protects the wearer, okay, the user, from outside, okay, but for clean room purpose, it protects the environment, okay, from us actually, because we are a dust carrier, to be exact. Okay. For the fifth slide, we can see the what are the what are the things that should be worn by the user when you are in the clean room. Okay, like you have all the, okay, the safety glasses, okay, the what I call the glove, the mask and everything, okay, and also the rubber shoes. Why we need the rubber shoes? Because the rubber shoes will have some static electricity, so it will attracts the dust, okay, attract dust, okay, and also other type attract dust, okay, and dust is an enemy in the clean room actually. Okay, that's the reason why. We go to the next slide after this. Okay, so for this slide we can see that, okay, 1 micron is 1 millionth of a meter, okay, and a human hair can have a size of 5 microns to 500 microns in diameter. So you can see that, okay, all our MEMS, okay, have a size lesser than 5 microns, okay, have a lesser size, some are lesser than 5 microns, some can be up to even like 1 millimeter, okay, depending on what type of device you are going to make, okay, and even sometimes, okay, especially nowadays, okay, we are dealing with the nanometers devices. So just imagine how horrible it will be, okay, if one hair, one dust, okay, fall onto your device. So that's why you need to wear such a clean room garments, okay, to protect actually your devices. Okay, you have done a lot of works, okay, you have done a lot of works, a lot of things you have done, and unfortunately, okay, the dust, okay, your hair or any other what I call debris from your body fall onto your device, so you have to start all over again. So that's why you need to, okay, you need to wear all those garments to protect, okay, your device and the environment from the dust that you may carry, okay, you may carry out. And you need to remember that, okay, this dust, okay, apart from spoiling your work, another thing is that the microelectronics devices are sensitive to this, okay, they are sensitive. And you just imagine lah, your or like from your simple calculator even to your mobile handphone, okay, if let's say one chip is affected by one of the dust, your device will be spoiled. So that's why you need to be very careful, and you need to wear all this protection and try to avoid this dust from your device. Okay, for slide 7 you can see that, okay, how horrible it can be. Okay, this, okay, showing figure 8.4, figure 8.4, okay, there's one human hair on an IC surface. So you just imagine one hair fall onto us an IC, okay, and compared to your IC lah, to your IC integrated circuit, not your kad pengenalan. Okay, your IC. So what happened there? Okay, so it's like the hair is like 10 to 20 larger from one feature, okay, from one micro structure. So just imagine how it can spoil your work after your hard work. Okay, so you need to make sure that those unwanted particles, okay, would not affect your works. For the slide 8, okay, now we go to something that is more like okay, related to the exam, related to the test lah. Okay, just now, okay, although I've been what I call very deep into the reason why you need all to wear the clean room garments and everything, okay. But for me, actually, the most important part in the previous slide is the definition of MEMS, okay. And then how you are going to differentiate between all those type of terms, like if let's say a question come out on the agro MEMS, bio MEMS and so on, okay, you can play around, okay, as long as you have those three component, which is it is a process technology, it is a electronic and it's electronic and a mechanical base, okay. It involves integrated chips, okay. Then your answer will be perfect, okay. Now we will go to another section of the lecture, which is the photolithography, okay. So it comes from the word lithography. Lithography means stone writing, okay. Like you have seen like for Malaysian history, okay, Malaysian history and so on, okay. We have batu bersurat, and then we can see ancient civilization, they carve on the stones, they carve on the stones, okay. So lithography in Latin, okay, in Latin means stone writing, stone writing. So since then, okay, this lithography, they use the term, okay, to describe, okay, the work that you are going to do in microfabrication. Okay, so what is photolithography? Okay, photolithography means that, okay, in this process you will temporarily coat photoresist on the wafer. Okay, you will temporarily, this photoresist is just for a while, okay, and then after that you transfer your wanted design, okay, design pattern to the photoresist. Okay, so whatever type of you want the resistor, you want your resistor, your BJT, anything, okay, so you transfer those design to your photoresist, okay. And this is the most important part in the integrated chip fabrication, okay. This is the most important part. But for this slide, okay, the most important thing that you need to remember that it functions, okay, how does it work? Okay, it works by temporarily coat the photoresist on the wafer, and then you transfer the design pattern to the photoresist, okay. So, okay, this photolithography process, okay, will determine the minimum feature size, okay. So it determine, okay, how big do you want, okay, how small you want the size of your structure, okay. And this process, okay, will take like 40 to 50%, okay, of the total wafer process time. Okay, for the next three slides, which are the slides 10, 11 and 12, okay, I will introduce you to the basic lithography process steps. Okay, for this slide, okay, first of all, we will clean the substrate, okay. Usually the substrate is made from silicon, okay. Just imagine the silicon wafer that you always see, okay. And then, okay, you have another one, which is silicon chips. Silicon chips we usually dice it. We usually just dice it, okay, from the silicon wafer, okay, to make a silicon chip. Okay, I think you know about you can if you can't imagine it, okay, you just browse, okay, you Google, okay, you just browse the internet, okay, to see the silicon wafer, okay, and then maybe you can see how they make a silicon chip out of the silicon wafer, okay. And okay, the first process of all is to clean the substrate. You clean it, okay, usually, commonly by washing it with an alcohol, with ethanol or methanol or isopropyl alcohol, okay. Then you blow it with a nitrogen nitrogen gas, and then you dry it, okay. Because first of all, okay, you don't want any dust or debris, okay, on the substrate, okay. And after that, okay, after you have completed the first step, then you will coat the substrate, okay, with the photoresist, okay. In this case, okay, for this slide, the next slide, and after the 12 slides, okay, we will use a positive photoresist, okay, positive photoresist. Okay, usually this photoresist comes in a form of solvent, okay. It can be transparent, okay, transparent. It can be in red color, okay. And in this process, okay, you will bake it lah, okay. You put it in the oven on the hot plate, okay, on the hot plate. In this process, okay, in this baking process, you will remove some solvent from it, okay. Some solvent of it, and it will be harder. It will be harder, okay. It will be harder than before. Okay, after you have already baked, okay, this is your call is soft bake, okay. After you have soft bake your photoresist, okay, you will align the wafer, okay, the photomask, you will align the photomask to the wafer. Okay, here, okay, then you will expose, okay, your wafer, your pattern, okay, through the photomask using a UV light. So you can see in the picture, okay, this UV light, okay, will react with your resist, with your photoresist, okay, and this will create pattern there, okay. You create pattern there. Okay, after that process, okay, after you have exposed, okay, your photoresist on the substrate, okay, what will happen then? You will have a post exposure bake. Okay, you bake it again. Okay, the reason why you want to bake it again, okay, bake it usually for this type of baking, okay, the soft bake and post exposure bake, it will it is like 40 degrees, not more than 80 degrees, okay, not more than 80 degrees, especially for the post exposure bake. The reason why is that you want to take off more solution from the photoresist, and the other reason is that you want to reduce the standing waves, for the next process. Okay, then after you have made the post exposure bake, okay, you develop. Okay, how? Okay, this section is interesting. Okay, I know for your generation is a bit even for my generation. Okay, in my generation, is when you hear the word develop, okay, it's some sort like quite alien for us. Okay, but if you see the old drama, old movies, especially the 70s or early 80s, okay, how they make pictures? Okay, they make pictures by rinsing, okay, the negative film, okay, of your picture, okay, by using certain chemical. So when they rinse, okay, they wash the film, okay, then you get the picture. So this is the same technology that they use. It's an old technology, but it's still it's a useful technology. It's an old technology, but it's a useful technology. Okay, after you have developed, okay, you will have your pattern. Okay, you will have your pattern. Okay, then you will have the optional hard bake. Okay, this is another baking process. Okay, this is another baking process, and the reason why we have this hard bake, which in some application it is an optional. Okay, but it is good actually, because it may enhance resistance to chemical or physical attack, because after this you will have other processes such as etching, where sometimes you will put metal, not sometimes, usually most of the time you put metal on it. Okay, you put a metal on it. Okay, so okay, during this etching process, okay, you need your photoresist, your hard already photoresist, okay, to be tougher, so that if like let's say you will have other processes, it can withstand the process. Okay, after you have already do your hard bake, okay, you will inspect, check your image, okay, and see whether all the pattern is in place. Okay, all the pattern is in place. For the 13th slide, okay, I would like to summarize the basic steps of photolithography. Okay, first of all, you have the photoresist coating. Okay, then you have the alignment and exposure of the wafer together with the photoresist on it, okay, to the UV light, and after that you will develop it. Okay, so these are the three important points, okay, of the basic. This is the three basic steps of photolithography. Okay, but for the next slide we will elaborate more on these three steps. But first of all, if you want to remember what are the basic steps of photolithography, you need to remember, okay, these three steps first. So the 14th slide is the more detailed steps of the photolithography process, where the first to the fifth steps are related to the first steps lah. Okay, to the first basic step, which is the photoresist coating. Okay, for the first step is the wafer cleaning. Okay, for the wafer cleaning, then you do the dehydration bake. Okay, wafer cleaning, like I told you, okay, in the first in the 10th slide, where you clean your wafer or your chip, okay, with the alcohol, with an alcohol solution, and then after that you blow it. Okay, that is the wafer cleaning. Then, okay, you do the dehydration bake to make it faster. You can just leave it in the in the fume hood. Okay, but this won't be good because it may create some standing wave on your wafer. Okay, so it's better for you to do the dehydration bake. Okay, and then you have, okay, this is optional. Okay, you apply the HMDS, hexamethyl disilazane. Okay, this process, okay, is good if you have a problem to make sure that your photoresist is attached to the wafer. Okay, usually you will have this HMDS to enhance your coating. Okay, and after that, okay, you coat your photoresist on the wafer. Okay, then you soft bake it. Okay, you soft bake to remove some solution and to make it more tougher. Your photoresist will be tougher. Okay, the next step is the align expose. Okay, although it seems that, okay, just one step, but actually in real life this is, okay, if you do it manually, this is the most sakit pala lah. Okay, this is the most what I call the toughest, and so give you a lot of headache. Okay, a lot of headache because you have to align. Okay, we will see like somewhere in the slide 40 something lah, 40 or 39 Okay, so you need to align it. Okay, you need to align, and then after that you expose it to a very strong UV. So during this exposure, okay, you need to wear glass, okay, anti-UV glass, because the UV that you are going to use is very, very strong. So it's maybe like 100 times stronger than our sunlight. If you are exposed to it, okay, you may get blind, so you must be careful. So this is one of the safety measure that, okay, you should take precaution while working in the clean room, okay, during this photolithography process. Okay, after you have already exposed it, okay, and then there's also a relation between how long you are going to expose and how strong is your UV, okay, with the photoresist. Sometimes if you use a thick photoresist, okay, this thick photoresist may need more time for exposure. Okay, it can take like 1 minute. Okay, but for the thin photoresist, maybe 5 seconds or 10 seconds will be enough, or even like 2 or 3 seconds, depending on the application. Okay, so alignment you need skill, okay, to do the job, to do the work, okay, and then the exposure, okay, you need to know the relation between the exposure of your UV light and also your photoresist, and then you have to wear, okay, apart from your clean room garment, you need to wear protection, glasses or face shield even. Sometimes we do have face shield, okay, to protect us from the UV light. Okay, and then you have the development. Okay, this development also needs skills, because like I told you, it depends on the what type of photoresist you are using, and also the thickness of the photoresist, the thickness of the photoresist. Okay, so if the photoresist is thicker, you need more time to develop it. You need more time to develop it. Okay, if it is thinner, okay, so you need lesser time. Okay, so it can be like, okay, like not more than 5 seconds to process it, and sometimes it takes more, okay, depending on what type of photoresist you are going to use. Okay, after you have, okay, there's some mistake. Okay, maybe the post exposure break is after the exposure lah, after exposure. Okay, so it makes sure that maybe your like a photoresist is more sturdier, it's more tougher before the development. Okay, and then after that, okay, after you have developed, okay, after you have developed, after the development process, okay, you do the hard bake to make sure that it is more your what I call your work, okay, can withstand the other process that for instant etching and so on lah. Maybe you need to do metallization and so on. So okay, the hard bake will help, okay, your work, okay, to be more tougher. Okay. Okay, for the 15th slide is just more like an elaboration of why you need the dehydration baking. Okay, first of all, you need to remove the moisture from the wafer surface. Okay, why you need to remove the moisture? Because okay, moisture on the wafer will reduce the resist addition, so it can peel off. Okay, and also okay, this if you have oxide surface, okay, it will allow wet etchants to penetrate easily between the resist and the wafer surface. So if let's say after this you are going to do like etching using certain type of acids, okay, nitric acid, okay, either fluoric acid and so on, okay, you may, okay, it can penetrate easily between resist and wafer surface, and this won't be nice for your work. Okay, and usually, okay, for dehydration bake, your parameter is temperature, so maybe you need somewhere like, depending on the application, okay, depending on the application, maybe you need it to like around maybe 50 or 60 or 80, depends on the application. Okay, for this slide, okay, for HMDS prime, okay, reason why you use the hexamethyl disilazane, okay, you want to promote the addition of the photoresist to the water surface. So the parameter you are going to use here is usually the timing for the spinning. You're going to spin the HMDS prime, okay, on the wafer. Okay, for slide 17, don't worry lah, you have like 19 parameters, so you don't need to memorize the whole thing. Okay, but okay, please do read each of it, because these are the parameters that is important during the photoresist coating, because all these parameters is important for you, okay, to determine the quality of the of your photoresist while you're coating the photoresist on the wafer surface. Okay, but I hope you can read all of this, okay, so that, okay, you know the importance, okay, you know the importance of each of these points, and also you make sure that the thickness you want, and also the uniformity of the resist, okay, can be maintained. Okay, so we have already like learned, okay, the process that usually applied in the in the photolithography. Okay, now we go to specific subtopic. Okay, subtopic for the microfabrication. Okay, for the for the photolithography. Okay, which one of it is the photoresist. Okay, photoresist is one of the important component. Okay, to make your pattern. To make your pattern on your wafer or your chip. During the microfabrication. So, what is photoresist? Okay, photoresist is made from a photosensitive material. So, it is okay. Like I told you before about how to develop a negative film. Okay, if you still remember just now. Okay, so the same principle also applied here. Here you are going to use a photosensitive material. Okay, photosensitive material. Okay, because you intend to temporarily coat it on the chip or your wafer surface. It's not forever. Okay, just for a while. Okay, although some application, okay, you may want it to be permanent. Okay, but usually you just want to temporarily use it. And then you are going to refer it. You are going to what I call. You want to remove it. I'm sorry. You want to remove it after this. Okay. So you will transfer the design image. Okay. You will transfer the design image on it through exposure. The exposure to the UV light. Okay. So like I told you. Okay. The technique. Okay. The principle is similar to the photosensitive coating on the film for camera. Okay. Photoresist. Okay, we can categorize photoresist. Okay, here by two category, which are the negative photoresist and also the positive photoresist. Okay, so this is a very popular questions that always come out. Okay, for the mid semester. Okay, for the quiz. Okay, so you need to know about this. Very deeply. Okay, so for negative photoresist, okay, what are the characteristics? Okay, what are the characteristics? It's okay, it will becomes insoluble after exposure. Okay, it becomes insoluble after exposure. So after exposed, it becomes insoluble. Okay, when developed, okay, the unexposed parts, okay, will be dissolved. Okay, when developed, the unexposed parts will be dissolved and it's cheaper. Okay, my tips, if this question comes out, okay, first of all, you just remember the first one it is a cheaper type of photoresist. Okay, it's a cheaper type of photoresist. Okay, but okay, if other questions come out, especially for the application of photoresist, usually the question will ask you, okay, the difference, okay, between negative and positive photoresist. Okay, for positive photoresist, okay, it becomes soluble. It becomes soluble after exposure. Okay, remember after exposure from UV light. Okay, when developed, the exposed parts that will be dissolved. Okay, when developed, the exposed part will be dissolved, and usually it has a better resolution. Okay, so another way of making notes of it. Okay, so positive photoresist should be expensive. Okay, and negative photoresist will have a less quality resolution. So there's another way of answering the question. Okay, again I repeat again. Okay, the characteristic of negative photoresist, okay, becomes insoluble after exposure. Okay, when developed, the exposed parts will be dissolved. Okay, it's cheaper, but the disadvantage is that it will have a lesser resolution. Lesser resolution than the positive photoresist. Okay, so how about positive photoresist? It becomes soluble after exposure. Okay, when developed, the exposed parts dissolve. It has a better resolution. But okay, disadvantage is that it is more expensive. So for slide 20, okay, these are the photoresist characteristics. Okay, summary of it. Okay, so for negative photoresist, okay, it is made from polyisoprene polymer. Okay, for positive photoresist, okay, it is made from novolite resin. Okay, so okay, for the photoreaction, okay, that happens for the negative photoresist is, okay, what happened there, okay, it's a polymerization. When it is exposed, okay, it will polymerize, okay, so it will create a chain together, okay, it will be harder, okay. For positive photoresist, okay, there will be a solubilization, okay, so it will solubilize the photoresist, okay. So this is what happened, okay, during the reaction. Okay, the sensitizer, okay, for negative photoresist, it creates free radicals, provide free radicals for polymer cross-linking. So it will have a cross-linking, okay, of the polymer, okay, and then, okay, for the positive photoresist, it will changes film to base soluble, okay, and both of these photoresists, okay, usually have dyes, okay, to color it lah, to make a difference. So okay, like I told you in the beginning, usually the negative, okay, may not have dyes lah, but it depends, okay. Usually the positive photoresist will have a red dye, so it will have a red in color, okay, because you want to differentiate between these two type of photoresist. Okay, for the slide 21, okay, please study the diagram. Please study the diagram. Okay, and also all the details about about the how the formation and the positive resist, okay, the oxide, the substrate, and so on. Okay, for this first part, okay, and usually for this type of questions, okay, if it just involve the process, it may the marks that will be given is around 5 to 6. Okay, 5 to 6. Okay, usually for the first part, okay, for the first part, okay, usually you get like 2 marks. 2 marks depends. Okay, so you need to have all the things lah. You need to label, and remember, during the exam you need to label. That's the thing that you have to remember. Never miss one label. Okay, so that you can get your full marks. Okay, then you go to the exposure. Okay, here you need to, okay, it's also the same, okay, nearly the same. Okay, so that's why, okay, for this is like what we call sedekah lah. We can say like a sedekah lah. Okay, for this type of question, usually for the first two parts, unexposed photoresist, exposed photoresist, usually students get right marks, all full marks, but comes to as long as you label everything correct lah. Usually you get it wrong, during the last one. Okay, so be careful, because like I told you, okay, when you develop the positive photoresist, the one that is exposed will be soluble. Okay, for negative resist, the one that is exposed that is maintained. Okay, because for the positive resist, you will have a solubilization. Okay, and for the negative resist, you have polymerization. Okay, so those keywords that you need to remember, polymerization for the negative, and the solubilization for the positive. Okay, you need to remember that, and you need to remember that by heart. Okay, and please practice this diagram. Okay, because okay, this is the basic for the microfabrication. Okay, for slide 22, okay, this is just about how you're going to control the thickness of your photoresist. Okay, the thickness of your photoresist. Okay, so now what will happen is that, okay, you apply your photoresist, PR photoresist, okay, your photoresist, okay, then you start to spin it, okay, okay, if you see the vacuum pump, okay, the vacuum pump, the function of the vacuum pump is to suck your wafer, and so during the spinning, you see the spinning is fast, okay, slow spin is 500 rotation per minute, it's not slow, So and then you can add it up, you can ramp it up to 7,000 RPM. So you just imagine. So if you use a slope spin, you will have a thicker photoresist. If you want it thin, so make it faster lah. Okay. So like for instance, for a thick photoresist, you want it like maybe like 3 microns, 5 microns, maybe like 500 to 1000. Okay. You use that, okay, using a thick photoresist. But if you want a thin one, okay, maybe more than 2000, more than 2000, you can have a thick one. You can have a thin one, So it depends on your application, how thin you want to be. Okay, maybe just 5 microns, okay. Not 5 microns, maybe like 2 or 3 microns. So it depends on your application.